We know that when we have endogenous explanatory variables, then the OLS estimator will be biased and inconsistent. This lecture will introduce a new estimator called an instrumental variable estimator, or IV estimator for short, and we'll do it first for the simplest case with a linear regression model with just one explanatory variable that happens to be endogenous. So that's the setup of the lecture. A linear regression model, we have random sampling, y depends on just one explanatory variable, but the problem here is that x is exogenous. The expected value of the error term conditionally on x is no longer 0 for all observations, and we know that that means that OLS will be biased and inconsistent. Standard errors will be inconsistent and inference cannot really be trusted. So as a concrete example, suppose that y is income and x is education. In such a model, it's highly likely that education will be endogenous because there will be other variables that affects income collected in the error term, and it's very likely that education will be correlated with those error terms. So when we estimate this equation using OLS, hoping to estimate the effect of 1 year additional education, keeping other variables constant, we will not be able to do that because as education increases by 1 year, we will have other indirect effects from other variables that are then also affected by the change in the level of education. So to handle the problem, we make use of something called an instrumental variable. So an instrumental variable is simply a new variable. Let's call it z. It functions as an instrument for the endogenous variable x in the linear regression model if the following conditions are satisfied. First of all, this instrumental variable z must itself be exogenous. It cannot be correlated with the error term. The expected value of the error term conditionally on the level of z must be 0. Second, it must be correlated with the explanatory variable x that is endogenous. So the correlation between the x variable and the z variable cannot be 0. And finally, it cannot have a direct effect on the dependent variable. That is, it should not itself be included in the regression model. That means that the conditional expectation of y given x and z does not depend on z. If all these conditions are satisfied, then z is an instrument for x. A common example of an instrument for education, the z variable, would be the level of your mother's education. It's reasonable to assume that this variable is exogenous. The level of your mother's education will probably not be correlated with factors that affect your salary, your income, but which are collected in the error term. Zi is correlated with xi. There is plenty of empirical results suggesting that the level of education of a parent is correlated with the level of education of the child. Finally, Zi will not have a direct effect on Yi. It's hard to claim that the level of your mother's education will directly affect your income. The effect is only indirect in the sense that if your mother has a high level of income, it will be correlated and make it likely that you have a high level of income and therefore generally a higher income. Now it turns out that the higher the correlation is between the instrument and the endogenous variable, the more useful the instrument will be. So we use the terminology, we say that the instrument is weak if the correlation is small, and it's a strong instrument if the correlation is large. So once we have a linear regression model with one endogenous explanatory variable, and we have identified an instrument for this endogenous variable, we can do the instrumental variable estimator. So the IV estimator for beta 2 is not the same as the OLS estimator. The IV estimator is calculated using this formula. The first thing that you can note is that the IV estimator uses the information from both the y variable and the x variable, but also from the z variable. Another thing you can see is that if I use my x variable as an instrument for itself, that is, if I let z be equal to x, then the IV estimator will become exactly the OLS estimator. So it's actually possible to prove that this estimator is consistent even when x is endogenous, as long as the instrument is exogenous and correlated with the x variable. The estimator for beta 1 will not change, it still looks like this. So let's have a look at how to do IV estimation using Gretel. Here I have a data set of just roughly 3,000 individuals. A lot of variables, but we're just going to focus on a couple of them. Ed is the education in years, and wage is the salary. And we also have the instrument that we will use, which is mom ed, that's your mother's education. So if I run a regression using OLS and I explain wage using, not here, wage as your dependent variable, and we use education as the explanatory variable, simple linear regression model using OLS, then these estimates are questionable since we would suspect education to be endogenous. Before we use mother's education as an instrument, we have to convince ourselves that it is indeed correlated with education. So if I do data, actually it's in view, correlation matrix, and we pick education and mother education, we see that they are indeed correlated, correlation of 0.4. And Gretel also actually tests the hypothesis that they are not correlated, and that is soundly rejected. So assuming that the level of your mother's education is exogenous in this regression model, we can do the IV estimator. And the IV estimator in Gretel is found here just below ordinary least squares. We have instrumental variables, and the one we're talking about right now is two-stage least squares. I'll come back to that in a second, why it's called two-stage least squares. But we pick that one, and you see that you get a new box, and that's the box for instruments. So we want again wage to be the dependent variable. I want education to be my x variable, and as an instrument for education I want mother's education. Press OK, and you can see that the effect is quite significant, from 29 something to 45 something. But you can also see a general result that follows when you do instrumental variables, and that is that the standard error has gone up quite significantly. So this estimator is, or I should say this estimate comes from a consistent estimator. To do IV in eViews is equally simple. Just do quick estimate equation, change the method from least squares to two-stage least squares, which is the IV, and you also get a box for the instruments. Type your equation, wage 76, constant, and ed 76. Type the instruments, which is mom ed, I think it's called, and do OK, and we have the IV estimator. So let's just quickly look at this issue for why the IV estimator is sometimes called the two-stage least squares estimator. Let's set up an auxiliary regression where we explain x, our endogenous variable, using the instrument. So xi is some gamma 1 plus gamma 2 times zi plus some error term nu I. This is like an auxiliary regression, meaning that it's not really a regression that we're interested in per se. So we're running a regression where we try to explain our level of education, and the explanatory variable is mother's level of education. So we estimate this using OLS. That will give us estimates G1 and G2 for the gammas, and I can find fitted values. I can get xi hats, the fitted values of this auxiliary regression. Now, if I run a new regression, a second regression, and I run it with y as my dependent variable, salary depends on theta 2, and I use my fitted values of education instead of the actual values, plus some error term running out of symbols. That's called the error term tau I. If I run this using OLS, then it turns out that the estimator of theta 2, the OLS estimator, will be exactly the same as the IV estimator of beta 2. So you can find the IV estimator of beta 2 in this regression model using OLS twice. That's why it's called two-stage least squares. The first regression, you have to find fitted values. This is the first regression. You have to find fitted values, and then you run a second regression also using OLS, where the fitted values are your explanatory variables. This process will lead you to the same estimator of the IV estimator. So as a final topic, let's look at a simulation study to demonstrate that the IV estimator actually works. So here I have done a new simulation study. First, I start out by just simulating data for an instrumental variable. I've done a very simple thing here. I just simply simulate from a normal distribution with a standard deviation of 2. Then I've continued simulating data for the error term in our regression model, and that too is simulated using a normal random variable with standard deviation of 1. Note that there is no connection between the z and the epsilon. That's important because I want my z, my instrument, must be exogenous. So there is no correlation between the error term and the instrument. Next, I simulate data for my explanatory variable. So the thing here is I want my explanatory variable to be correlated with the error term, making it endogenous. But I also want it to be correlated with the instrument. That's one requirement for z to actually be an instrument. So you can see that what I have done here is simply just taking a linear combination of a and b. So the x variable is basically a weighted sum of z and epsilon. I've just used some weights such that the variance of the x variable is 4, just like the z variable. So the instrument and the explanatory variable has the same variance. And since x is partly determined by z and partly determined by the error term, it will be correlated with both. So now x is really endogenous and z is really an instrument. I have calculated the sample variance of the z data in this cell H2. Remember, the true variance of each one of these random variables is 2 squared, so that's 4. I have calculated the sample variance in the error term, and the true variance of the error term is 1. Here is the sample variance in the x variable, and the way I have calculated x, it will also have a true variance of 4. And if I just F9 a couple of times, we'll see that yes, that seems about right. Next, let's check these sample correlations. So here in H5, I have the sample correlation between the z and the x variable. They must be correlated, and they are. Sample correlation about 70%. You can actually show that the way I have done this, the true correlation between them is 1 over square root of 2. Similarly, the error term and the x variable are correlated, so the x variable is endogenous. The sample correlation 0.68, and you can show that the true correlation is the same, 1 over square root of 2. So I've made the simulation such that the x variable is equally correlated with the error term and with the instrument. If we focus on these ones, we can see that it makes sense, right? These are approximately 0.71. If I just F9, we can see that yes, that seems to make sense also. So let's simulate some y data. And I have simulated y data from a very simple regression model. I have set beta 1 equal to 0 and beta 2 equal to 1. So y is just 0 plus 1 times the x variable, c2. Note that, that's important, plus the error term. So y is indeed determined by the x variable, and the x variable is endogenous. So we would expect the OLS estimator to be biased. So let's check that. Here I have calculated the OLS estimator of B2, and just to make life simple, I have run a regression of y on the x variable, but I have set the intercept to 0, so I'm just estimating beta 2. And this is my estimator. Remember, true beta 2 was 1 and B2 is 135. So let's F9 a couple of times to see if this is unbiased or not. 132, well, you can clearly see that it's biased. It seems like it's somewhere between 1.3 and 1.4, so it has a bias upwards of about 40%. So let's do the IV estimator in Excel. I have two options. I can either just use the formula for the IV estimator, or I can use this two-step procedure. So let's do the two-stage least squares. So here I have done the regression where I run explain z using the instrument. So that's the OLS estimator in the first regression. Based on this regression, I have calculated fitted values, as you can see here. That's just the OLS estimator times the x variable, sorry, the z variable, and that gives me the fitted x values. Again, I have set the intercept to 0 to make it as simple as possible. And finally, the IV estimator, Well, that's a regression explaining y, not with x, but with x hat. So the final step here is that I've done that here. That's my regression, but now I have explained y with x hat instead. That's my IB estimator. And let's check now. If I F9 this one, you can see that it is indeed unbiased.